Hi, this is Mike Mulholland, and today we're going to be doing a proof of the Pythagorean Theorem. So we're going to do it based on a right triangle, with each side also being one side of a square, projecting from that side. You know what the Pythagorean theorem states, and it's been known from before 1500 BC, but as far as we know, it wasn't proven until Pythagoras or one of his students sometime around 500 BC. It's quite important to math. It has over 400 known proofs, including by a person who was a president of the U.S. in the 1880s. So a proof that I devised is worked out below. It's highly unlikely I'm the first person to come up with it. And if I am, I'm sure there are others out there that are quite similar, some of them quite old. Another tutor posted a very short answer that suggested just that. And when I submitted this question to Wyzant, there wasn't seem to be a way for me to add a diagram, and there didn't seem to be a way for me to do so for a written solution either. So that's why I'm making my answer a video so I can use images. This is the image that I had in mind that you could do from my description of the problem. I would have liked to get to one of the steps further along before cutting you loose to try to go further, but it would be hard to describe those other images, so we're stuck with this. So we have this triangle with sides x, y, and z, and so each one, the side of the triangle x has a square attached to it, also with sides x. So the area of this square is x squared, this one z squared, this one y squared. So to prove the theorem, we'd need to prove that the area of this square is equal to the sum of the area of this square and the area of this square. Although you may have come up with some other way of doing it, since there are so many. Okay. So the first thing I did is I took the blue square and moved it over until its left edge instead of its right edge was aligned with the side of the triangle. I moved the yellow one up, same idea, until its bottom edge instead of its top edge was aligned with this edge of the triangle. And then the green one I left where it was. So next we extend each line that ends within the overall figure to the edge of the overall figure. Like, for example, we extend this line from there on over to here. And now we label the vertices. I'm only doing that for the vertices that turn out to be relevant to the proof. And now we're going to have a way to talk about the various shapes and angles. We know that the area of the green square is z squared because this side is z, length of the side is z. And again, we're trying to show that the area of the blue square plus the area of the yellow square is equal to that. Now, what appear to be right angles at the marked vertices are right angles. For most of these, we know they are because they're at the corner of one of our squares. This one, it's a little bit more indirect. We know it is because it's a corner of one side of a square, and then this line is parallel to another line of the square because they are both extensions of sides of this square. And this vertex would be similar explanation. So if it looks like 90, it is 90. So I've put some red lines on here to define 1, 2, 3, 4 triangles within the green square, and then a central square within the green square. So we're going to calculate the areas of the pieces and add them up. We'll do the triangles first. Let's call the measure of this angle ABC theta. That's the symbol for theta. And then if this is theta, What's that angle? Well, that's a right angle. So that's 90. So then we got this one's going to be 90 minus theta. But then this is a right angle here from there to there. So if this is theta, this is 90, so 90 minus theta, then this is theta again. And so on around we go. So we end up with this for our angles. So we know that each of these triangles has the same angles. And we know that the hypotenuse of each of these triangles is the same because it's equal to the hypotenuse of our original triangle, the side of the green square. So now, can we prove that all four of those triangles are congruent, and therefore have the same area? We can. There's various ways to prove they're congruent. So let's see which one or two of those we could use in this case. Side, side, side. Now we only know one side. Side, side angle. No, we only know one side. Side, angle, side. So we have 90 minus theta, and we have z, and we have theta. So we could use this one. Angle, side, angle. Yes, we could use that one. Whoops, sorry. I got carried away with my circling. It was this one that works. We know two angles and one side. There's my eraser. Erase that mark. Okay, do we know whether angle, angle, angle would work? We know three angles, but it's not any good. Why not? Because we can have triangles with the same angles that are not the same size. So those are called similar rather than congruent. So that's no good. Angle side side is no good. Why not? Because you can have an angle and a side. So we know this goes off this direction. But if we have a given side length, sometimes what will happen is it could be like that, or it could be like that, and they both work. So that's no good either. Hypotenuse leg, does that work? Yes. We know, no, not in this case, I'm sorry. But what is it? It's really one of these in disguise. So if it's a hypotenuse, what do we know? If it's a hypotenuse, we know it's a right triangle, and therefore we know one of the angles is 90 degrees. So we have two legs and an angle, and so it's an example of that side-side angle. This is just a special case of it when it's a right triangle. Okay, so here we are. So we've established that all four of the triangles outlined in red have the same area, but what is that area? Okay, let's do this triangle because they're all going to have the same area. So we do that. Its base is the same as the width of the yellow square, which is y, and its height is the same of the height as the side of the blue square, which is x. And the formula for the area of a triangle is base times height over 2. So in this case, it's y times x, or x times y over 2. And since there's 4 of them, we multiply by 4, and we get 2yx, or 2xy, is the total area of all 4 of the triangles. Now we've got the square here. What's the length of a side? Well, the length of a side is this case, x is the length of the blue, but then we've got that is y. So the length of this side right here is x minus y. And so the area of this inner square, we take the length of a side x minus y and square it. And if we expand that out, we get x squared minus 2xy plus y squared. And the total area of the green square, we got to add the area of the triangles, which is that. But this cancels that. And so we get x squared plus y squared for the area of the green square. And we said that if we could prove that, we would have proved the theorem. So we did. We just proved the Pythagorean theorem. And thanks for watching, and take care.